All right, today we're going to talk about something that sounds super simple, but is actually fascinatingly complex: how we measure ships. You'd think, it's just length, width, and height, right? But it turns out every single measurement tells a really important story about engineering, about safety, and even about how our entire global economy works. So let's dive in. So, let me just ask you a question right off the bat. Take a look at this ship. How long would you say it is? Well, the answer is a bit more complicated than you might think, because in the world of shipbuilding and naval architecture, there really isn't just one single answer. It all comes down to why you're asking the question in the first place. See, before you can measure anything at all, you need a starting point. Everybody has to agree on where zero is. Think of it like a 3D coordinate grid that gets laid over the entire ship. This is the fundamental blueprint that makes sure a designer in Hamburg and a pilot in Singapore are talking about the exact same thing. And the absolute floor of that grid, our 0 point for anything vertical, is called the baseline. It's a perfectly horizontal line drawn right at the top of the keel plate, which is kind of like the ship's spine. Every single vertical measurement we're going to talk about starts from this line. Okay, so that's our vertical zero. Now, what about the horizontal? For that, we use the summer load line. This is the official water line. It shows the maximum depth a ship can be loaded to, specifically in summer seawater, which is less dense. This line is a huge deal for safety. It basically defines where the ship sits in the water. Okay, now that we have our floor and our water line, we can create the official bookends of the ship, at least for calculation purposes. These are the forward and aft perpendiculars. You just imagine a vertical line going up from where the front of the ship, the stem, hits that summer load line. Then you do the same thing at the back, where the rudder post is. Those two lines are your bookends. All right, our grid is set up. Now we can finally start measuring. Let's tackle the first dimension, length. And as you're about to see, just having one number for length is definitely not going to cut it. First, we have what's called length overall, or just LOA. And this is exactly what it sounds like. It's the absolute, no-nonsense, tip-to-tail measurement. If you were going to put the ship in a giant bottle, this is the number you'd need. It's all about physical clearance, and it's the measurement the port authority cares about when docking the vessel. But for the engineers, the people who actually design the ship and need to make sure it's stable and efficient, there's a much more important number. And that is the length between perpendiculars, or LBP. Remember those bookends we just set up? The LBP is the exact distance between them. This is the length naval architects use for all their critical calculations. So let's just put them side by side to make it super clear. LOA is for the physical world. It's the will it fit in the parking spot measurement. LBP is for the world of physics. It's the how will this thing behave in the water measurement. They're two totally different tools for two totally different jobs. Okay, that's length covered. Now let's talk about how wide a ship is, or as it's called in the maritime world, its breadth. And yeah, you guessed it, just like with length, the devil is in the details. First up, there's molded breadth. The key word here is molded. Think of this as the internal width of the ship. It's measured from the inside of the ship's frame before you add the thickness of the outer steel plates. And why would you do that? Well, because this number tells you the actual usable volume you have inside for things like cargo. And then you have extreme breadth. This is the opposite. This is the full, external, absolute widest point of the ship, including the thickness of those steel plates. This is the number you need to know if you want to get through the Panama Canal. It's the ship's true side-to-side footprint in the world. And this diagram just lays it out perfectly. You can see right there, the breadth molded is measured inside the frames. That's your usable space. But the breadth extreme is the whole shebang. It might only look like a few inches difference on each side, but trust me, when you're navigating a narrow channel, every single one of those inches counts. So we've done length, we've done breadth. Now let's move on to our final axis, the vertical one. And here, we need to get really clear on the difference between two very important ideas. A ship's depth, that's its total height, and its draft, which is how deep it's actually sitting in the water. This is a great little overview of the key vertical dimensions. You've got the draft, which is the whole part of the ship that's under the waterline. Then there's the freeboard, which is the part you can see above the water. And finally, you've got the air draft, which is all about making sure you don't hit anything overhead. Let's break them down. Let's start with draft. And just like with breadth, we've got an inside and an outside version.
The molded draft is measured from our internal starting point, remember the baseline, down to the waterline. But the extreme draft, that's the one that keeps you from running aground. It's measured from the absolute lowest point of the entire ship all the way up to the waterline. That's your true clearance underneath.
Now let's talk about the part of the ship you can actually see, the part above the water. Freeboard is that distance from the waterline up to the main deck. It's a super important safety indicator. The less freeboard you see, the heavier the ship is loaded. And then there's air draft. This one's pretty simple. It's the distance from the waterline to the very highest point on the ship. And you absolutely better know that number before you try to sail under a bridge.
Okay, but a ship isn't just a giant floating box, right? A huge part of its strength, its stability, and its ability to handle rough seas comes from some really subtle but absolutely essential curves. So let's look beyond the box for a minute.
First, take a look at the side profile of a ship. See that gentle upward curve of the deck as it goes from the middle out towards the front and back? That's called shear. And it's not just there to look graceful. Its main job is to help the bow and stern lift over waves and keep tons of water from crashing down onto the deck.
Now, if you were to look at the ship from head-on, you'd notice the deck isn't perfectly flat from side to side either. It has a slight arch higher in the middle. This is called camber, and it's a brilliant two-for-one design. It adds a whole lot of structural strength, and just as importantly, it makes sure any water that does get on deck drains right off the sides.
So, LOA, LBP, molded breadth, freeboard, shear, camber. I know, it can feel like a whole lot of jargon, but it's so much more than that. This is a precise, shared language that answers the most important questions you can ask about a ship. Will it fit? Is it stable? And most importantly, is it safe? This language is literally the foundation that allows global trade to happen. And that kind of leaves us with a final thought to chew on. If every single one of these dimensions we've talked about is actually a clever engineering solution to a specific problem, like stability or capacity or safety, what are the new problems that the ships of the future are going to have to solve? And what new kinds of measurements will we have to invent for them?